Hi there, and welcome to the lesson on vectors, and specifically it's this time around, the title's about to pop up, the scalar product. Okay, so now let's just move on to a warm-up on the next slide. So here we've got a warm-up. We've got points A, B, and C have position vectors 1, 2, 3, 4, 3, minus 1, 13, 6, minus 3. So again, they're in the form of column vectors, and they say position vectors, so meaning that they originate from point O. So the origin is 0, 0, 0. If they're position vectors, they originate from the origin. Here I asked to find AB. So here's AB, A to B, and then BC, and BC. Deduce their collinear, meaning in the same line, and find the ratio of AB to BC. Okay, so in order to find AB, so AB is here, so AB will be minus A plus B, or B minus A. So AB is like going negative of OA, or AO, you could say, plus OB. So there we go. So the negative of this one, so if this one goes from O to A is 1, 2, 3, then from A to O is minus 1, minus 2, minus 3. So that's why we've got minus 1, minus 2, minus 3 for this one, and then plus that one. So from O to B is this one, so plus OB, and then minus 1 plus that is that, minus 2 plus 3 is 1, minus 3 plus minus 1 is minus 4. So we've just found AB. We're going to do the same with BC. So BC is like going BO plus OC. And BO is a negative of OB, so it'll be negative 4, negative 3, plus 1. Plus C is 13, 16, and negative 13. And then that plus that is that. That plus that is that. That plus that is that. So we've found AB and BC. We're going to deduce that they're collinear. So AB and BC, so to be collinear, they have to first of all be parallel. So we need to check, are these scalar multiples of each other? So let's see, to make 3 become 9, we need to times by 3. So 1 by 3 times 3 is that, minus 4 times 3 is that. So basically, BC is 3 AB. They're collinear as they're scalar multiples of each other, as I said. So therefore, if this one is, like for example, 1, and this one is 3 times as long, so if this one is 3 times as long as that, then the ratio of this one to that one is 1 to 3. Because I said find the ratio of AB to BC. AB is the shorter one, BC is the longer one. So AB to BC is 1 to 3, because this one's 3 times as long as that one. Because they're scalar multiples of each other as well. Prove they're parallel. Here's another warm-up. Feel free to pause it and try it yourself, because it's just review of earlier topics. In the diagram, the point C on OA, sorry, here's OA, here's the origin. So the point C on OA is such that OA is 3 times as long as OC. So if all of this is 3 times as long as OC, then this must be 1/3 of the whole length, and this one must be 2/3 of the whole length. And point D is on OB, such that OB is 4 times as long as OD. So if this is 4 times as long, this must be 1/4, and this must be 3/4. So I've got 1/3 here of that, and 1/3 the length of OA. That's 2/3, 1/4, 3/4. AD and BC meet at E, so they cross at point E. OA is A, OB is B. So this one must be 1/3 A, this one must be 2/3 A. This one must be 1/4 B, this one must be 3/4 B. Expressed in terms of A and or B. Don't forget to have the little lines under the A and the B. OD. OD is this one, so we've kind of already worked that out. So feel free, if that whole thing is A, you can have a little line under there. This must be 1/3 A, this must be 2/3 A with a little line under there. This whole thing is B, this one must be 1/4 B, according to the information here, and this one must be 3/4 B. So these fractions are all because of the information that was in there. So therefore OD, as you can see, is just 1/4 B. OD is 1/4 B. Please put a little line dash under there to indicate that it's a vector. OC, sorry, OC is this one. We know it's 1/3 A. OC is 1/3 A. Please put a little line under the A, don't put it under the third, put it under the A, because that's the vector part, this is the scalar part. CB, 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 you could work it out as being minus this plus that. So minus the third A plus B, minus the third A plus B. Please put a little line under here and a little line under here. Maybe do that here. It's fine if you also wrote B minus the third A. That's okay as well. Where's DA? DA is the same as going minus a quarter B plus A. So minus a quarter B plus A, put little lines under there, is the same as A minus a quarter B. Please put a little line under the B, a little line under the A to indicate that they're vectors. Okay, moving on to the scalar product. What on earth is it? So there's a little formula in your formula booklet, and you're going to be using it a bit here. So the scalar product is mainly used to determine the angle theta between two vectors. Try to think, what is V with the lines either side of it? That's right, it's not the absolute value, it's the magnitude. So magnitude of vector V times magnitude of vector W cos theta. And what on earth is this? Let's see. We don't know yet what this means. So we've got vector 1 and we've got vector 2. Basically, what would be the angle between those two vectors? That's what we use the scalar product for. So just pointing out again here, you can have an X, Y, Z kind of plane, and you can have point P in a three-dimensional plane, point Q, and there can be an angle between. So in those two vectors as well. So it can be an angle in a two-dimensional plane and in a three-dimensional coordinate system. So the formula is defined as V dot W equals magnitude of V times magnitude of W cos of the angle between them, where theta is the angle between vector V and W. But what is V dot W, that thing, and those two things? We already know from the past that they're the magnitude of V times the magnitude of W. But V dot W is a thing called the scalar product. So you might find kind of in other books like the dots drawn a little bit bigger. This one is a bit small, but normally it's drawn tiny bit thicker than the one there. So the scalar product, here's a formula that you'll be using a lot to solve for the angle between two vectors, but you need to be able to know what this is. It's called the scalar product. And how do you calculate a thing called the scalar product? So you use V1W plus V2W plus V3W. What on earth does that mean? So meaning that if it was in this is if it was in a three-dimensional plane. So V1 W1 times that by that plus that by that plus that by that. That's how you calculate the scalar product. So this scalar product just turns out to be like a nice little number. This ends up being just a number, which is calculated by that times that, plus that times that, plus that times that. It's called the scalar product. So basically, a lot of the time you're going to be asked to rearrange this formula and solve for theta. So you need to find out what the value of the scalar product is, these two magnitudes, and basically do the scalar product, divide by these two magnitudes, and then cos minus 1 of that. So if you were to transpose this, so scalar product, remember, if you replace scalar product with what it actually is in a three-dimensional coordinate system with 3D vectors, V1, W1, V2W plus V2W, basically I've subbed in, I've replaced this with the scalar product, I've divided off the two magnitudes, and then you would cos minus 1 the answer to get theta. Some things to remember. The scalar product is quite often called the dot product. So in our book we use scalar product, in some books they use dot product. And possible to also call it the inner product. The one I tend to use is, I quite often will call it the dot product. The dot product is the terminology I use in Australia. I used to use in Australia a lot. But you can use scalar product or dot product, doesn't matter. When the two vectors V and W are perpendicular, so imagine that the vectors had a 90-degree angle between them. Therefore, you'll end up getting a dot product of 0. Because cos of 90 degrees equals, according to your unit circle, remember you've got your unit circle, and cos of 90 degrees is up here. Cos is 0. There's no, the x-coordinate of a point on a unit circle as you spin 90 degrees that way will be 0. That's what cos of theta is. So therefore, if the angle is 90 degrees between the two vectors, you'll end up with a dot product of 0, because cos of 90 equals 0. So if you end up with a dot product of 0, you know automatically that the angle between them was 90 degrees. So if you were asked to prove that two vectors were perpendicular, you'd find their scalar product and prove that it's 0. So that's something that is useful to remember. That comes up a bit. Another different thing to remember is when the angle between vectors v and w is acute, meaning like less than 90, between 0 and 90 degrees, then cos of theta is greater than 0, and therefore the dot product would be greater than 0, so meaning it wouldn't be a negative. So if it's an acute angle, so if you were asked to prove that basically the angles between two vectors are acute, you could find their dot product and prove that it's greater, that the dot product is greater than 0. More things to remember, so many things to remember in this. When the angle between two vectors is obtuse, so between 90 and 180, then, similar to the other one, when they're acute, the cos theta and also the dot product is greater than 0. When they're obtuse, cos theta and the dot product are less than 0. So maybe the question just says the dot product's less than 0, what can you deduce about the two vectors? You might say that the angle between them is obtuse. Another thing is the dot product of a vector and itself is equal to magnitude of, if you sub it into the formula, it's a magnitude of vector times the magnitude of the same vector. So, which would be vector squared times 1, which equals v squared. Similarly, I dot I equals 1, because the magnitude of the unit vector is 1. So that makes sense, because remember a unit vector, by definition, has a magnitude of 1 if it's called the unit vector. I dot I equals 1, because 1 times 1 equals 1. So regular vector v times v, magnitude of v times magnitude of v, and so on. Yeah, anyway, moving on. Here's an example. Feel free to try it for yourself if you want, because it might be easy enough for you already. So find the scalar product, or the dot product, of each of these pairs of vectors. So to do it, I tend to find it easier to write them as column vectors. So these are in ij form. I would write them in column vector form, because then you just remember it's that times that plus that times that. Same with this one, it's that times that plus that times that plus that times that. So 2i plus 3j, write it as 2, 3, dot, so dot product of 1, 6, that kind of thing. So I tend to write it like this first, and then you do 2 times 1 plus 3 times negative 6, and you've got negative 16. So you found the scalar product of that one. What can you deduce about the angle between the two of them, according to some of the earlier slides? Just think about that. Because the answer is negative, the scalar product is negative, what can you deduce about the angle between them? Not that you're asked to calculate it at this point. So for B, I would say rewrite them as column vectors as well. 4, minus 2, 1. 4, minus 2, 1. In dot product with 2, 1, minus 3. So you do that times that, plus that times that, plus that times that. C just helps you visually a bit. So that times that is that times that is that, plus that times that is that. What do you get? You get 3. So you've got a dot product that's positive, greater than 0. What can you deduce about the angle between those two vectors then, according to those earlier slides? Is there something there that could tell you? We don't know exactly what it is, but we can say what type of angle it is. Oh, and there's the last one, by the way. Last one was already in column vector form, so you do that times that, times that, times that. Oh, sorry, that times that, plus that times that, plus that times that. Write it all out, you get 13. Again, it's positive, so what can you deduce about the angle between those two vectors? Find the angle between the vectors v and w. So here we actually need to find the angle. So you might want to find the scalar product, dot product thing first. So you might want to write them as column vectors. And then you need to find the magnitude of v and the magnitude of w, sub it into the formula, and so on. So that's the formula that you need to sub it into, which is in your formula booklet. VW equals VW, and so on. I'm pretty sure it's in your formula booklet. I'm just going to have a quick double check. I'm not losing my mind. Yes, it is in your formula booklet and written just like that. On top of that,
they write that formula, and they also write v dot w equals v1 v1 plus v2 v2 plus v2 w2 plus v3 w3. They also give you the formula for remembering the scalar product, meaning that they give you this in the formula booklet, and they give you that. Fabo. Okay, so we've got to find the dot product. So find the dot product first is what I do, because that's dead easy. I prefer to write them as column vectors first. I'd write it as 2, 1, 1, and 1, negative 1, 3, and then do that times that, plus that times that, plus that times that. Show some working out to get your method marks, and you've got 4. So we need to work out the magnitude of v now to sub it. So we've worked out this bit is 4, so we're going to sub this as 4. Now we've got to work out these two values. Magnitude of v, use Pythagoras in 3D. Square root of 2 squared plus 1 squared plus 1 squared. Get root 6. Let's work out the magnitude of w now. Square root of 1 squared plus negative 1 squared plus 3 squared gives you root 11. So you're going to sub in, what's root 6 times root 11? That's right, it's root 66. Woohoo! Okay, so substituting into equation 1, we put our 4 here, we've got root 6 here, we've got root 11 there. Remember, root 6 times root 11, and it's cos theta, don't forget that. Root 6 times root 11 is root 66. So therefore cos theta must be 4 divided by root 66. And then they want you to solve for theta. So theta will be cos minus 1, 4 over root 66. And if you plug that in a calculator, get your little calculators out, make sure you're in degrees mode. In this case, make sure you're in degrees mode, and do cos minus 1, 4 over root 66. Just in case people don't know how to do that, I suppose I better show you. Please have your calculators with you, because if you don't, you're just not going to be good at remembering how to do stuff in the exam. Make sure your mode's in degrees for this one. Yay, good-o. So go second cos. I like to do fractions, but you can just do 4 divided by root 66. Where is the square root sign? I've lost it, oh my gosh. Square root 66. Alright, out of there. Aha. Okay, so write out the unrounded answer, 60.5037 blah blah. Write out the unrounded answer, and then to 3 sig figs it'd be 60.5 degrees. Make sure to write that. Yay. Another example. Given that the two vectors, v equals 3t plus I, blah, blah, and w equals this, are perpendicular meaning that they form a right angle, find the possible values of the constant t. This is a really, really classic exam question. Because you know, if they're perpendicular, what does the dot product have to equal according to the things to remember? Slide back here. When two vectors are v and w are perpendicular, theta equals 90 degrees and cos 90 equals 0. Therefore, the dot product equals 0. So you can come up with little formulas for the dot product. Okay, so write them out. You might want to write them out as column vectors, but just remember it's that times that plus 1 times 3 plus negative 1 times negative 2. Write them out as column vectors first if it helps, and then write out the dot product. So that times that plus 1 times 3 plus negative 1 times negative 2. Then FOIL all this rubbish. So when you FOIL this, you'll get 3t squared plus 9t minus t, which gives you, I'm on the second, sorry, plus 9t plus t, so it gives you plus 10t. Then you've got plus 3 plus 3 plus 2. 3 plus 3 plus 2 is 8. So whoopee-doo, we've got this. So now what we've got to do is find the constant value t. So we need to therefore factorize this quadratic. You could, at this point, if it was non-calculator, you'd look for a common factor. There is no common factor. Then if it was non-calculator, you would try to do the splitting method. 3 times 8 is 24. What's a number? What's two numbers that multiply to give 24 and add to give 10? So multiply to give 24 and add to give 10. So think 24. What is there? There's 24 and 1. There's 12 and 2. There's 6 and 4. That's right, you've got to use 6 and 4. So you'd go 3t squared plus 6t plus 4t plus 8. You need to factorize that, and then work it out. And then when you do that, you would end up with 3t plus 4t plus 2 equals 0. So then separately, if t plus 2 equals 0, then t equals minus 2. If 3t plus 4 equals 0, then 3t equals minus 4. So t equals minus 4 over 3. So solving gives t equals minus 4 over 3 or t equals minus 2. So the possible values of t are minus 4 over 3 and minus 2. So I said this is a really classic exam question. If you forget how to do it, if it was with calculator, you could instead just solve it really fast on Polysmalt. Remember, you go apps, go to Polysmalt, wherever it is on your calculator, enter Poly Root Finder, not simultaneous equation solver in this case. 2 is the order of the polynomial because it's a quadratic. Highest power is a 2. So you've got to put in 3, 10, 8. Just reminding people how to do that. 10, 8. Solve, we solve. Then you've got minus 2, 4 over root 3. If you wanted it decimals, you can change this button. Changes it to decimals, fractions, that kind of thing. Fraction, decimal. See, same answers. But that could have been done non-calculator. So this probably would have been a non-calculator question. So practice doing a splitting method. So on the side, even though it wasn't written on here, on the side working out, show the splitting method for how you would get this. Remember that times that is 24. So you split this into 6 and 4 and separately factorize them and blah, blah, you get that. Okay, so here's the proof of this formula. Do we just accept this formula is mathematically sound, or do we demand to see how it works? So this is not part of your course, but in case it's of any use to you, here's a proof. So I'll just quickly kind of beam it up. So we've got the formula. So imagine we had two vectors, a1, a2, and vector b, b1, b2. So that's its x, its y, that's its x, its y. Translate one of the vectors so that they both emanate from the same point. So from here, here's a, here's b, and here's the angle between them. This vector, therefore, so this resultant vector here going in this direction would be minus a plus b. Nice, minus a plus b. That's a nice way of writing that is b minus a. And it has the length, so magnitude b minus a. So it'd be the magnitude of b minus a is the length of that one. And this looks kind of like a cosine rule kind of problem. So remember the cosine rule? C squared equals a squared plus b squared minus 2ab cos theta. So we can say that this thing, because we know this thing is that, the length of this one is that. Therefore, that one squared equals this one squared, so the magnitude of a squared plus the magnitude of b squared minus 2 times the magnitude of ab cos theta. So you're sort of seeing where it comes from. It comes from the cosine rule. And then there's other sorts of stuff that you can go through, but b minus a, so b minus a is this minus this, so you can write it as b minus that, or b minus a, there you go, b2 minus a2. So b1 minus a1 squared plus b2, b2 minus a2 squared equals all that kind of stuff. You can expand that, minus 2ab cos theta, and so on and so on and so on, basically, which ends up simplifying, all this stuff ends up simplifying. Okay, thank you. We'll finish there though.